All right, kiddos, this is the Unit 5 review, Assignment 5M. What I'm going to do in this video is I'm actually going to break this video into two different parts. This is a pretty long review, so for time's sake, what I'm going to do is I'm going to cut this review into two pieces. I'm going to do the first 3 pages, and then I'm going to do the last 3 pages. So the first 3 pages will get us all the way, let me actually jump forward, all the way up to problem number 63 here. And then on the other one is where the page change turns, and then we begin again. So we'll get done with this first section, and then we'll get done with the second section in the second video. All right, so without further ado, let's go ahead and start reviewing. The first questions are asking us to find extrema on the closed interval. And so in 1 through 8, find the absolute extrema for the functions on the closed interval used for graphing utility. So for absolute extremas, when they bring this topic up with absolute extremas, what you need to do is you need to do the candidates test. So you find all the important pieces, but ultimately you're going to be doing the candidates test. All right. So we begin by finding any critical pieces. That's where derivatives are equal to 0 or are undefined. So this is going to be 2x plus 5. So if I set this equal to 0, I see that I'm having a critical moment at 5 over 2. All right, so that's the only critical part. So to find absolutes, again, what we have to do is the candidates test. So what we're going to do is we are going to test the original function at -4, -5 over 2, and 0. So what I do is I test any critical points, including the endpoints of the interval that is given. And so from here, I really don't mind if you use a calculator on the test, even if it's no calculator section. It's just because this is arithmetic, and it's just for time's sake. All right, so -4 gets us an answer of -4. -5 over 2. Gets us an answer of -6.25, which is -25 over 4. And then 0 gives us an answer of 0. Okay, so with these places, these points in place, I can identify the absolutes. So I notice that the absolute maximum out of this would occur when the y value is 0, so that occurs at the point 0, 0. And the absolute minimum at this, in this criterion, is when the y is equal to -6.25, so that would be -5 over 2, -25 over 4. Okay, so those are our absolutes in this particular case. Okay, number 3, I take the derivative, so this is going to be 1/2 x to the -1/2, or aka square root of x on the denominator with 2. So what I notice is x cannot be equal to 0. That would make the denominator equal to 0. Also, x has to be greater than 0 as well, because you can't have a square root of a negative. All right, so those are criterion in this situation. So what are the critical points? We're going to test f of 0 and f of 4. Okay, so it didn't create any critical points in there because we were already going to be testing 0. However, we test 0. Okay, anyways. So using the number 0, we have the square root of x minus 2, which is going to be negative 2. Testing 4, we get an answer of 0. All right, so what that shows us in this criterion is that the absolute max is going to occur when the y value is 0, so that's going to occur at 4, 0. Okay, the absolute min occurs when y is negative 2, so that'd be 0, negative 2. All right, last but not least, number 5. Okay, here we go. So the derivative in this situation, the derivative is bottoms up, derivative of the top, minus, leave the top alone, derivative of the bottom, all over the bottom squared. So doing some math up in here, we have 4x squared plus 36 minus 8x squared. So this ultimately is going to be equal to negative 4x squared plus 36 all over x squared plus 9. Just a little bit more neatly. Sorry. X squared plus 9 squared. All right, so that is the derivative. Let me kind of minimize some of this stuff to get some more working room here. Okay, so again, we still need to find the critical points of this. So the denominator is not going to do anything for us. We can't make x squared into a negative 9 somehow, so we don't worry about that. The only critical numbers that are going to come off of this is when this thing is straight up equal to 0. So when is 4x squared plus 36 equal to 0? So this would leave us with x squared equals 9, so x is equal to plus and minus 3. Plus and minus 3 are the critical numbers. So when you put in a square root, you have to put in a plus minus. Okay, so with this, we need to test out our endpoints and any critical numbers in those in that interval. So that would be negative 4, negative 3, positive 3, and positive 4. And again, these go into the original equation. So negative 4 into this equation is 4x divided by x squared plus 9. And that is negative 0.64. Seems like an odd number, but whatever. Okay, let's try negative 3. Okay, this is what, negative 2/3. Trying positive 3. Positive 2/3. And positive 4. So again, positive, so this would be 16 over 25. I write decimals down just because it helps me identify, again, what is actually larger or smaller. So it gets kind of a little convoluted when you're dealing directly with just the fractions themselves. So I can easily and quickly see that 0.66 is smaller than 0.64. All right, so this is going to be my minimum, and then my maximum is going to be this 0.66. However, I'm going to report the fractions as my answer. So my absolute max is with positive, so that would be at 3 2/3, and the absolute min is going to occur at, sorry, distracting myself, -3 and -2/3. This is one that I'm going to check out real quick. So we have 4x divided by x squared plus 9. Okay, I believe it. It doesn't rise or fall very much, but you do see that it has a general sway to it. So okay, I believe it. All right, using the mean value theorem. So the mean value theorem states that it has to be continuous on a closed interval, differentiable on an open interval, and then the instantaneous rate of change is going to be equal to the average rate of change, aka a tangent is equal to the general slope. Okay, this one I don't think you can use the mean value theorem, and here's why. All right, so this is continuous, obviously. I think this graph looks something like that, and it's continuous. However, you can't take a derivative of this. So note that the derivative of this will state that this is going to be 2/3 x to the -1/3. So in this situation, notice that x cannot be equal to 0. All right. Oh, actually, no. So I'm sorry. This can be used. This can be used. X cannot be equal to 0. Now, if this interval were something like -3 to +4, something like that, something in which this would fall, then you can't do the mean value theorem. You can't use the mean value theorem. However, this is from an interval from 1 to 8, so the mean value theorem is back on the table. It's all good. So again, it has to be continuous on the closed interval and differentiable on the open. So this, what I was just in essence testing, is this indeed differentiable on the open? And yes, it is. The only point that is off the table is if there were a 0 in the interval itself. Okay, so mean value theorem. Mean value theorem is, in essence, the slope is equal to the tangent. All right, so let's find the average rate of change. The average rate of change is your general slope. So that's going to be f of 8 minus f of 1 all over 8 minus 1. So here is where I'm going to kind of use my calculator. Again, calculators are fine when you're just doing general arithmetic. Okay, so this is 4 minus 1 all over 7. So the average rate of change in this case is 3/7. I don't know where I got 3/7. All right. So the average rate of change in this situation is 3/7. Okay, the instantaneous rate of change is the derivative, and so I already described what that is. So that's 3/3 root x over 2. And then, so in essence, what the mean value theorem says is that the instantaneous rate of change, the tangent, is equal to the secant, which is equal to 3. Oops. The instantaneous rate of change is equal to the average rate of change. So in this situation, 2 over 3 third root x is going to be equal to 3/7. All right, let's cross multiply. So this is going to be 9 third root x is equal to 14. 14 divided by 9 is 14 divided by 9. And then take this to the third power. So whatever 14 divided by 9 to the third power is what x is. It seems like a ridiculous answer. Seems like a ridiculous answer. I might have done some bad math. Let me quickly just check my answer key. I apologize that it's, again, when you get a crazy fraction like that, that kind of makes me weary about if I did something incorrect here. So let's going to take a quick glance at my pre-described. Heck no, that's exactly what I got, which is kind of weird, but that's exactly the answer that is correct. Okay, so that is your maximum value right there. Excuse me, that is the C. So again, what the mean value theorem is in essence describing is this. If you have a graph of something, okay? You have a graph with something like that, and it's continuous from, like, for instance, 1 to 8. Okay, we have this line from 1 to 8. Okay, if you take a slope of that, there is going to be a point somewhere in between 1 and 8 that the slope of the tangent will be parallel. And this just so happens to occur at 3.7641. Okay, so at 3.7641, that lines up with the point of where the tangent is parallel to the secant, the arctan change. Get it back into a lesson. I'm sure you already knew that, because this is a review for the test. All right, so that is your value of C. Find all C's. That's the C. All right, here we go. This is continuous and differentiable. Identify any, in which is, okay, this is asking for increasing and decreasing. So this is straight up just the derivative. So any critical points, we see that there is a critical point at -3/2. So we do the first derivative test, and the point in question is -3/2. We test that against the derivative. So I see that, for instance, if I put in a 0, my answer is going to be positive. If I put in a wicked negative number, my answer is negative. And so they want to know, where is this increasing or decreasing? So this is going to be increasing when the derivative is positive. So that would be from -3/2 to infinity. Where is this decreasing? This is decreasing when the derivative is negative. That's -infinity to -3/2. Okay, find any critical numbers, find any open intervals, increasing, decreasing, apply the first derivative test, identify all extrema, and okay. So we're finding maximums and minimums in essence. Okay, so what we do is we find any critical numbers. So that's where the derivative is equal to 0 or it's undefined. So in this situation, we see that x is equal to 3 would be a critical number. What we do now is we take those critical numbers and we do the first derivative test. So I'm testing positive 3. So when I test this, I see that if I put in a 0, for instance, my answer is negative. If I put in a huge positive number, my answer is positive. So this is going to be a minimum. Okay. However, this is asking when is this increasing and decreasing. So increasing from 3 to infinity. And this is decreasing from negative infinity to 3. And then identify all relative extrema. So as I said, I have a relative minimum, at least, when x is equal to 3. So all I need to do is find the y coordinate, and that you go back to the original equation itself. So when x is equal to 3, my y value is going to be -4. Okay, same idea with number 31. Let's do the purple. So we take our derivative of this, and so this is going to be t to the third minus 8, and so that would mean t, critical numbers would exist when t is equal to 2. Okay, so there's our critical numbers. I don't know if I have to really specify that, but let me just make it more clear. Critical numbers. That's 3, all right? Critical numbers. T is equal to 2. All right, just to make it blatantly clear, so if somebody was grading me, they don't have to understand mathematics to know what the answer to the question was. Like I can show an idiot this thing, and they'll know what the critical number is. Right. Onward. So let's do this on the first derivative test. I guess this is h. And so I'm testing the number positive 2. Testing the number positive 2, I see if I put in, for instance, a 0, my answer is going to be negative, and a really big number, and my answer is going to be really positive. So this is, again, going to be a minimum, decreasing to an increasing. So this is increasing from 2 to infinity, and decreasing from negative infinity to 2. Okay, so that lets me know that I have a relative minimum when x is equal to 2. Match this up with the y coordinate. So when x is equal to 2, my y coordinate is going to be -12. Finding points of inflection, find points of inflection in the concavity. So inflections are when second derivative is equal to 0 and also switches from positive to negative or negative to positive. So second derivative is where it's at. So we'll get there yet. All right, so first derivative comes first. And this is going to be 3x squared minus 18x. All right, second derivative of this thing is going to be 6x minus 18. So critical numbers off of this second derivative would be when x is equal to 3. So testing this, so it is indeed equal to 0. So let's see if it switches from positive to negative or negative to positive. So x in the second derivative, I'm testing the number positive 3. So if I test a number like 0, for instance, my answer is negative. And if I test a really big number like 5 or something like that, I see that my answer is positive. So this is a concave down to a concave up, and it is indeed equal to 0 at 3. So yes, this is a point of inflection. So I have a point of inflection when my x coordinate is equal to 3. But for a point, I also need the y coordinate to go along with this. So I go back all the way back to the original equation, and I find my excuse me, I find my y coordinate, which is at negative 54. Okay. So here's the third page. This is the page that I'm going to end with today, and then I'll pick it up the rest with the second part of this video. Okay, so let's find any critical points, and that is where this derivative is equal to 0. So the derivative of this equation is going to be 1 minus sine of x. So where is that equal to 0? And so that would be where sine of x is equal to 1. Where is sine of x equal to 1? Let's take a look. Sine is the y coordinate, and so I see that sine is equal to 1 at pi over 2. So there is a critical number at pi over 2. All right, that is in the realm that I have here. So that is our critical number. All right, let's go ahead and put this on the test. So let's take a look here. X and the derivative, and we are testing out, it starts at 0, ends at 2 pi, and we're testing out pi over 2. So putting in a small number, I see that my answer is going to be really small. It'd be less than 1. And so if that's the case, then my answer is positive. Oh, hold on. Yeah. Oh, I'm sorry. I'm looking for points of inflection. I'm sorry. I'm silly. I'm sorry. I'm looking for points of inflection. I'm not done yet. Oh, great, googly, googly. Come on, Ashton. All right, so I'm looking for points of inflection. I'm sorry. So that is a second derivative, and so this is going to be negative cosine. Okay. And so I'm not looking for a 0 with the derivative. I'm rather looking for the 0 of the second derivative. All right. So this is making a lot more sense. Okay. So cosine is the x coordinate. And so I am going to have critical numbers at pi over 2 and 3 pi over 2. And so doing the second derivative, if I'm plugging in x's of my second derivative, okay, again, it starts at 0, goes to 2 pi. and I am checking out pi over 2 and 3 pi over 2. If I put in a small value, like, like pi over 4 or something like that, and I plug that into the second derivative, I get a negative number. Put a number in between the two, like pi, for instance, and I get a positive number. Try something a little bit larger, like 11 pi over 6 or something like that. Oh, shoot, I'm sorry. There it is. And again, I get a negative. So this is asking for find the open intervals in which, excuse me, wrong question. Like, where are the points of inflection? Find the points of inflection and discuss the concavity. All right. So I see that this is concave down, concave up, concave down. I'll call that as my discussion. You should probably actually really be a little bit more formal than that, but I'll just kind of jump over it. And so I have inflections when I'm at pi over 2 and also at 3 pi over 2. And so when I'm at pi over 2, for instance, the cosine is equal to 0. So this would be equal to pi over 2. And at 3 pi over 2, the cosine is equal to 0. So this would be 3 pi over 2. There's your inflection points. And again, if you need to know the concavity, you can write what I wrote up there a little bit more formally. Okay, here we go. They want us to kind of make a graph here. So they give us some roots. So f of 0 is 0, and f of 6, 1, 2, 3, 4, 5, 6 is also equal to 0. The derivative is equal to 0 when x is equal to 3, and 5 is also equal to 0. Let's put that aside just for a second. I see that the derivative is greater than 0, aka it's positive when x is less than 3. So I'm going to go to 3, and I'm going to kind of draw attention to when x is equal to 3. So what this is saying is when x is less than 3, the derivative is positive, so it's increasing on this side. The derivative is also positive from 3 to 5, so we'll go to 5. And the derivative is still positive, so it's increasing on that. However, it's negative when it's greater than 5, so that means it's decreasing in that realm right there. So what that means is this: when x is equal to 5, it will have some. Okay, and I'm just going to make up a point. So when x is equal to 5, it has some derivative that is equal to 0. So this is, in essence, saying that this is a maximum. Now, if it's increasing from 0, in essence, to 5, and we have another derivative equal to 0, this is, again, what I call a hiccup, where you're going to, the derivative is going to level off, but it's going to continue up. Okay, the second derivative when x is less than 3 is negative. So that implies that this section is concave down. And then I have no idea what they're trying to say right here. I don't know what this is saying, so I'm just going to, I think this is going to say an and or, I guess. when it's greater than 4. I'm sorry. So this is going to be when it's greater than 4. So when it goes to 3, and then so this area over here is also negative, the negative, so this is also concave down. So this area is also concave down. Okay, sorry, last statement. The second derivative is positive, that means concave up from 3 to 4. So it's concave up right there. Okay, increasing concave down. Let's draw this picture. Increasing concave down, this will be a horizontal tangent, so something like that. Increasing concave up, okay, and then concave down. So so what I kind of think is going to happen is it's going to switch concavity like that. So it's concave down, and then we have to hit this 0, so it's going to have to take a sharp turn down through there. Something like that. Oh, very googly moogly. All right, optimization. So a rancher has 400 feet of fencing, which to enclose 2 adjacent rectangular corrals. What dimensions should be used so that the enclosed area will be maximum? So kind of like drawing an overhead view of this is what's going to occur. So I'll call these Y's and these big length X's. And so all of this is going to be, all of these X's and Y's are going to add up to 400 because that's how much fencing we have. And then we want to take the area into consideration. So let's start with the lengths of the fence. So the lengths of the fence would be 2 X's and 3 Y's is going to be equal to 400 feet of fencing. And then inevitably what we are working towards is what's the total area of this, and that is going to be X times Y. So I kind of made this a singular X, and that's a singular Y. I made my own rules. Okay, let's start back to the left here, and we see that, let's solve for one of these variables. Let's go with X. So 2X is equal to 400 minus 3Y. And then, so X is equal to 200 minus 3 over 2Y. Substituting that into the area, because we are going to maximize the area. So the area in this situation will have an X that is 200 minus 3 over 2Y times Y. So this is 200Y because I said so. Okay. Like that. All right, so let's maximize this area. So that means take the derivative and see where the heck that is equal to 0. Okay. So where is this equal to 0? I see that 3y is going to be equal to 200. I moved the equal sign, I apologize. And so y is equal to 200 divided by 3. We can come up with an actual measurement here in just a sec. Actually, let's do that right now. Okay, so this is approximately 66.666666 7 feet. Okay, that's approximately what that is. Now let's just see if that did indeed maximize the area. So I have to do the first derivative test with this 200 over 3. So mentally, that's approximately 66 something. So putting in a teeny tiny number, I see that my answer is positive. Putting in a really large number, I see that that answer would be negative. And so that implies that yes, indeed, that is a maximum. Hooray. So that is maximized. So that implies that the height of this thing is 200 over 3 feet, aka 66.66666. The x in this situation, let's just use a calculator here to help ourselves out. Oh, great googly moogly. Let's put this in for y. So this would be 200 minus 3 over 2y. And that is straight up 100. So let's, for good measurement, also say what is this maximum area? And this maximum area is going to be just x times y. So 100 times 200 over 3. I don't know if that will, yeah, it's 20,000 over 3. That's kind of ridiculous, but it's 6,666.6666 feet squared. Okay, that's where I'm going to end this video. The rest of the video will be on part 2, or the rest of the review will be on part 2.